I have the great pleasure to introduce Araceli Bonifant from the University of Rhode Island. And I heard rumors that there might be surprise appearances, perhaps not. So you're going to talk about where rabbits go when they escape or something like that, right?
Rabbit escape region. Yeah. Thank you. Okay, so I have some invitees to my talk. My collaborator that is not visible, I don't know where he went, John Milnor, and Pascal, because they wanted to say hi to Karsten and congratulate him. So you want the congratulations now or later? When do you want the congratulations? Now? Okay, Jack, you can go ahead, Jack.
Okay. Well, I'm very jealous of all you people in Rio. I wish I could be there, and I hope Karsten has a wonderful celebration. The program sounds wonderful, and I hope you all have a good time, and congratulations, Karsten.
Thank you. And we also have Pascal. Pascal, do you want to say anything?
Yes. So I am very sad that my family succeeded to put COVID, I don't know to say, on me. And I'm very sad not to be with you. And I'm looking at the TV to participate somehow, but I cannot say happy birthday in person. And so I thank you for letting me this opportunity now. So happy birthday, Karsten, and enjoy the conference.
And we also have Scott. And he's the expert. He's the computer expert, eh? Scott, we don't hear you.
Scott, we can hear you.
That's because my microphone is broken. See, I'm the expert. My microphone is broken.
Okay.
So,
We hear you now. We hear you now. We heard you.
hear me now?
Yeah.
Okay. Well, anyway, so happy birthday, Karsten, and I'm really sorry I couldn't make it. Next time, I hope, for your 70th. And I can't say anything better than Jack said it, so that's the usual thing. So, anyway, happy birthday.
Okay, Jack, anytime that you want to interrupt me, please feel free to interrupt me. Oh, I have to look there. Okay. Good, I'm ready. I'm ready. Okay, so today I'm going to talk about, after all these introductions, I'm going to talk about the rabbit escape regions. And as I said, this is joint work with John Milnor. And okay, and now, well, I'm going to introduce the curve SP in case you don't know this curve. So this is the space of all monic center cubic polynomials with a marked critical point A of period P greater or equal than 1. And if this V is the critical value, then we obtain this normal for the curve, and this is the formula that we will be using in the computations. We can also identify the curve SP with a smooth affine curve that consists of these pairs AB in C2, such that A, which is the marked critical point, has period exactly P under iteration of the map. And it was recently proved by Kiwi and Arfo and Kiwi, sorry, that this curve P is connected. And we can also present this curve as a union of the connectedness locus plus the escape regions, a finite number of escape regions. So a map is in the connectedness locus, as you know, if and only if the Julia set is connected. And the map will be in the escape region if and only if the Julia set is not connected, as expected. And each escape region, you can think of it as biholomorphic to the unit, to the puncture disk. And the genus of this curve SP grows exponentially with P. You will see this very, very soon. Okay, so since we're going to be talking about the escape regions, we thought it was a good idea to present a map here, a cartoon representing a map in the escape region. So usually they have this equipotential, figure 8 equipotential. In one of the lobes, in this lobe, you have the mark critical point A, and over here you have minus 2A. And you have the co-critical point 2A. This follows the orbit of the free critical point, which is minus A. You have a ray, which is going to be called coperiodic ray that goes through the point 2A here. And if you take theta minus 1/3 and theta plus 1/3, these are rays that crash on the free critical point minus A. And one important feature of one of these is that one of these guys is periodic, but you never know which one, okay? And if the orbit of this mark critical point stays on one lobe of this figure 8 curve, then we're going to say that the escape region has 0 needing sequence. And they are the main players of this talk, the escape regions with 0 needing sequence. Okay, so following Branner and Hubbard, we know that there is a one-to-one correspondence between the period P hyperbolic components in the classical Mandelbrot set. This M is going to denote the classical Mandelbrot set, and that the escape regions in SP, which have a trivial needing sequence. And the easiest way of studying these components identifying these components is because they are the satellite copies of the main hyperbolic component of the Mandelbrot set, and they are in one-to-one correspondence with the fractions of this form, where there are no common factors between n and p can be greater or equal than 1. And here I'm showing a picture. Okay, so these are the components that are going to be called, where am I? These are the components that are going to be called the n over p rabbit components in the Mandelbrot set. And here is a picture of the Mandelbrot set. And over here, we are showing the rabbit region components, the 1/4, the 1/3, the 2/5, the 1/2. And there are other components that are marked here, which are no rabbit components, but they have 0 needing sequence. For example, the worm that is over there. This is the airplane right there, and you can see Cocopelli over there. So the airplane, this region, which is a 0 needing sequence, appears in S3, and this worm and Cocopelli and this double basilica that I forgot, they appear in S4. So let me show you. Okay, so I'm going to show you an example of a Julia set in the rabbit region. So from now on, I'm going to denote by E n over p a 0 needing region with rotation number n over p. And yeah, so we see that each non-trivial component of the Julia set in this rabbit region is going to be hybrid equivalent to the Julia set for the center of one MP rabbit component in M. So here is a picture. So this is an example of a map in the 1/3 rabbit region in S3. In the escape region, I mark here the orbit of the mark critical point. So this is A, this is f of A, and this is the image of the second iterate of A, and then goes back there. So this is, and then you can see here you can see here that there are many smaller copies of these that are converging towards the main component of this. So you can see them over there. And you can see the rays landing at the central point over there. Okay, so this is an example of the 1/2 rabbit region. This is the curve S2. And the basilica region is the one outside. It's a neighborhood of infinity. And inside, you have another escape region that, in this case, has needing sequence 1, 0. I will explain a little bit later what this means. I want to say that this, notice that this region has a boundary, this ring of hyperbolic components there. Right. And notice, okay, so, and this is the universal covering of S3. This is a torus, and I mark in this white curve like the fundamental domain. And you can see here that there are 8 escape regions, so 1, 2, 3, 4, 5, 6, 7, and 8. So the rabbit regions are just the rabbit, which is over here, and the -1 terabbit or corabbit that is over here. But we have another 0 region, which is the airplane region that I told you. And we have this region that was very important in the study of Arfo kiwi, because it's the only one that doesn't repeat. Okay, so this is S3, the covering, the universal covering of S3. And now, so Jack proved long time ago that this curve SP has 4 types of components, hyperbolic components. So the components of type A, if you have both critical points belonging to the same Fatou component, you have type B. If you have 2 critical points that belong to different components of a common cycle, then you have type C that has a property that any iterate of the free critical point minus A belongs to the cycle of attracting Fatou components of A, but minus A itself does not belong to that. And finally, type D components in which the critical points belong to disjunct cycles of attracting Fatou components. So these are important, and I mention them because in this picture, which is a close-up of the rabbit region in S3, they're going to appear. So you can see here that there are 2 type A components, and then you can see that there are 4 type B components enclosing the escape region of rotation number 1/3. I want to say that these angles right here have denominator 78, given by this formula. And I want you to pay special attention to the distance between, or to the width of the gap between between these 2 parabolic points that are the boundary limits of this type A component. So you can see that the distance here is 26, which is precisely 78 divided by 3. That is going to be important. So this is an example of a 1/4 rabbit in S4. So over here, again, the 1/4 rabbit region is a neighborhood of infinity. I want to say that in the previous picture, the rabbit region looks enclosed only because of the type of parametrization that we are using for the torus, okay? And over here, we're using canonical coordinates, so the 1/4 region or rabbit region is a neighborhood of infinity again. There are 2 type A components, which are these 2, and there are 1, 2, 3, 6 type B components here. And there are some parabolic points in the intersections of these components, or between those components. Now, as you know, like there are some pictures that are Photoshop. This is a Scotchop, meaning there are 8 escape regions in here, But when you draw the picture, so we had to draw the picture, one half, and then code it, and then Scott helped us to put this thing here, be dragons, so that you could see a nice picture of the one for rabbit. Okay, again, in this case, the denominator of the coperiodic race is 240. 240, and again, I want you to call your attention to the distance or to the gap between 2 and 82, which is 80. And you can see that 80 is divided by 240 is 1/3. Okay. Oh, yes, before I forget, so this S4 curve has genus 15, and it has 20 punctures. Laura DeMarco and Ron Shift, yes, long time ago, they did a program, they had a program to compute the number of escape regions in NESP. I don't know how far that is going, but it was very scary the last I remember.
We computed to period
26,
30,
maybe 30. Yeah. So, okay, so the rabbit theorem, well, as you expect, I'm saying that for each rotation number of the form 0 n over p minus 1, so the rabbit region is surrounded by a circle, as I was trying to illustrate, up to p hyperbolic components of type A or B. There are 2 components of type A and 2 p minus 2 components of type B. And for notation purposes, so we index these components, modulo for p, in clockwise order, and we go like 0, B2, B4, B, by even numbers. And I said there are some parabolic points in the middle, and in this case, these are indexed by odd integers modulo for p. And this is a cartoon of the escape region of the rabbit, the 1/3. You can see here the 2 type A components, and you can see the 4, so for a total of 6. And then you can see between them parabolic points, which are also the root of this type D component that is indexed by odd numbers mod for p. Okay, and I guess I just forgot to say that, but I guess it's obvious that every parabolic point, for example, P3, is between P2 and P4. So it's in the boundary of components of this type J minus 1 and G plus 1 mod for P. Okay, so this is the theorem of which we're going to sketch the proof. And the main lemma is the following. So for each rotation number NP, we're going to construct a ring of 4p hyperbolic components of types A, B, and D, which have a well-defined rotation number and which surround an escape region. And we're also going to compute the angles of the dynamic rays, which land at the central fixed point of these components. So we can specify all that. So to prove this, we're going to produce the corresponding Hubbard trees of these components of type A, B, and D. And we're going to start by using the notation ET will be, rotation by the angle T. It will be exponential to pi I T. And so if we are talking about the model for a type A or type B component, this model tree is going to have pHs. And each H is going to join the origin to a root of unity of this form, EK over P. In the type B case, and then instead of having pHs, we have double, we have 2 pHs, and then the tree will join the origin to a root of unity of the form EK over 2P. And here are examples of the trees. So the first one is an example for a B2 component. The second one is a tree for a D3 component, and the last one is an example for a B4 component in P equals to 5. So in all these cases, E0 is the vertex E0 has been labeled by the marked critical point A, and then we label by E over E j over 2p minus A. So this J is related with a type of component that you have over here. It's either type B2, D3, or D4. And it just expresses the distance between A and minus A. And the dynamics in these trees is given by multiplication by E n over P. Okay, so, and then we have a theorem of Fourier that says that each of these trees is realized by a critically finite map. And, well, we just need to pick up these critically finite maps belonging to SP, and we have the appropriate type A, B, or D, depending how many H's. But the thing with these trees is that we still have to work on them a little bit, because this map is only unique up to 180-degree rotation. So we have to make it a little bit better. So for that, we're going to talk about the flattened tree. So this is the tree that got fatter. And on this side, you can see the picture of the Julia set. And this part over here is what this cartoon represents, just the cycle of components around the periodic point. The angles are the same as there, and we are ignoring this part of the Julia set. So since we are since this is an example of a Julia set in a D1 component in E3 over 5, that means that the denominator of these angles is going to be 242, but this is, for the period. Not for the co-critical angle. So, and you can notice here that any gap of length less than 81 gets mapped to 3 times the length of the gap. For example, 3 gets mapped to 9, 9 gets mapped to 27, 27 gets mapped to 81. If you multiply 81 by 3, you see that you go around this whole thing, but then you cover a little bit more. So you cover one of these petals, either V or V prime, because you need to have 243. Good. All right, so now how do we compute the angles? How do we compute the angles that appear in this picture? Well, that's very easy. All what you have to do is, well, you assign the value of 1 to V and V prime, which are the images of the critical points, with a denominator 3p minus 1. And then, you know that if you multiply this angle by 3, you have to go to 3b, so you're going to assign f of b and f of b prime respectively, and you keep going from there. So these angles are uniquely defined up to an additive constant, and they also should satisfy the condition that if you have a gap between petals, if a gap between petals has this angle, then of course the image has to have the angle 3t mod 3p minus 1. Just by, so that everything works. And again, there are 2 possible solutions for this case, and they differ by a 180-degree rotation. Okay, so now I'm going to introduce another element. This is the triad that we have over here, and we go back to our picture for the sketch of a polynomial map in the escape region. So as I said, this angle theta is that goes through 2A, is the coperiodic angle. And as I said, one of these, either theta minus 1/3 or theta plus 1/3, is periodic of period P or Q in this case. And let's denote by, let's call theta Q, I think is what I'm going to say. Let's denote by theta Q the periodic angle, either theta plus 1/3 or theta minus 1/3, and theta q star will be the non-periodic one. Okay, so now in this picture, you see that they are crashing together at -a. But if I were a little bit inside the connected locus, you will see one ray crashing here in one corner of the component containing -a. This will move to the right. And then you will see the other ray on the other vertex right here. So we're going to construct a wall that we call the kneading wall that will be made up of this ray, the arc between the vertices of this component, and the other ray over here. So one it will be the periodic ray, say this one, this arc, and then the other ray right there. And as I said, this will be called the kneading wall. And this kneading wall, even from this picture, we can see that it divides the plane into pieces, one that contains the mark critical point A, and one that contains the point -a. And if I am in one side of this, for example, if I am on this side of the wall, all the orbit of the critical point, mark critical point, is on this side of the wall, containing this lobe, then we will say that it has kneading sequence 0 because you never go this way. Okay? You never cross the wall. Okay, so this wall will be famous in United States, but not here. But okay, so here I have that Julia said for the map. Over here you can see 2A, and you can see in this side are all the coperiodic rays that land at the root point of this component that contains 2A. There are usually here just 4 rays, so when you see the picture of the parameter plane, so the red is one of them, the blue is another one. I don't know if you can see the colors. There is a green one, and there is a purple one. And I drew in the same colors the corresponding periodic rays, which would land in this point, and the other ones over here. And then I drew an arc joining the vertices of the component that contains -a. And now you can see, for example, let's study the wall. Which one you see better, red or blue, or nothing? Okay, there is a red ray here, which is 334, and the corresponding rays for theta minus 1/3 and theta plus 1/3 is 92 and 576. Okay, so it's this one and this one. And now I'm going to construct the wall, so I'm going to follow this ray 576, and then I get to the periodic point, then I cross the component -a, U -a, and then I get out in this ray, which is not periodic, 92. And you can see that this wall is separating the orbit of the critical point from this side of the picture. Therefore, this ray, red ray, should be on a 0 kneading sequence. Similarly, if I take the blue ray here, which is 335, I have another two rays, the corresponding periodic one, which in this case is 93, and the other one, which is not periodic, which is 577. And you can see again that this ray separates the orbit of the critical point from the other side. So therefore, that ray 335 is also in the 0 region, in the rabbit region. But if I take another ray, say the purple one that maybe you see better, then you can see here that the corresponding periodic ray is 333, and the other ray is 91. So if I construct this wall going on the purple ray, so you can see that I'm separating A from the rest of the orbit. So this guy should have kneading sequence of the form one, what is the other guy? Here, one, I said purple, right? Yeah. So 1, 1, 1, 1, and then come back to 0 on this side. So I thought it was important for you to see where this point is coming from. So this is the parameter space, well, a piece of the parameter space. You can see all the mess that appears on the left side, but on the right side, you have the 3/5 rabbit region. You can admire that the red and the blue ray are in the place where they are supposed to be, and the purple ray right here lies on the region with Needham sequence that I told you, 1, 1, 1, 1, 0. Okay. Okay, so what we need to do? We need to prove that the escape region that we constructed is the required NP rabbit region. And well, we noticed that it's a 0 Needham region, as I explained before. And I said to prove this, you just have to compute the invariant for one of the parameter rays, which I already did. So I don't have to go over this again because I explained how to do it. Yeah. And so the next step is to what is it? Oh, here. So for the final lemma is, okay, so I have a map in an escape region. The orbital plus A is containing a connected subset of the field Julia set. I want to prove that this happens if and only if I am in the 0 Needham region. So I go back to my picture of or a sketch of a map in the escape region. And then I consider the nested sequence of compact sets, of nested compact sets like this. And X0 is going to be the closure of the loop containing the mark critical point A. And then this proof is just topological. You define the set Xi plus 1 as the invariant set under the map. So, and then you can see that if this E denotes a 0 Needham region, then the entire orbit is going to belong to every one of these Xi's. And because they are connected, and because this map F from Xi plus to Xi is a two-fold branch covering, then we know that each Xi is going to be connected. And so therefore, the intersection, just topological argument, is the required connected subset of the field Julia set that contains the orbital plus A. Okay, so what is next? Oh, on the other hand, what happens if E has non-zero Needham? Well, obviously, in that case, the orbit is not going to be contained just in one connected set. Good. So therefore, we are almost done. Then now we just show that the orbit of plus A is contained in one component of the field Julia set, and that it has rotation number n over p. And so now the only thing that we need to realize is that the only quadratic Julia set with periodic orbit of this period and rotation number is p is the quadratic n over p rabbit. And therefore, the escape region where we are must be an NP rabbit in SP. And this completes the proof of the rabbit theorem. Okay, so this was the main thing. And then I wanted to present some conjectures about this curve. These are not related to the rabbit regions. So this is more general. So if you just follow Dwadi and Hubbard, so we're going to use the term Mishurevich point for any map in SP so that, you know, the orbit of the free critical point is eventually repelling. And then Tanley proof for quadratic maps that if you increase the magnification, the connected locus of, you know, the Mandelbrot set around a Mishurevich point and the field Julia set of the map at the corresponding repelling point look more and more alike. So we claim that this conjecture, it also keeps in SP. So we know that we also have similarity between the connectedness locus at any Michelewicz point in SP and its Julia set into A. And moreover, all the rays landing at the point F will be at the point I better show the picture. So the rays also land in cyclic order. So let me show you the example. So this is a picture of a Michelewicz point in S4. Actually, this place over here is the Cocopelli. And this is the point 2A in the Julia set. And this is the point 2A in the parameter plane. And you can see here that the angles, I don't know if you can see, but the angles, the same angles land at the same point either in the Julia set or in the parameter plane. And they follow the same cyclic order in both cases, even though not all these rays belong to the same escape region. So these two belong to the Cocopelli region, but this ray belongs to a different escape region. Okay, so this is the conjecture. And then we also have a Mandelbrot copy conjecture. So this just says that every type D component in SP is containing a unique maximal copy of the Mandelbrot set. So over here, I'm again in a little piece of S3. This over here is the rabbit region. This is a parabolic point between them. This is the airplane region right here. This is 010 region, and this is 100 region. What matters is that if you go here, this is the 1/3, rabbit, the copy of the Mandelbrot set or component. This is the main hyperbolic component. This is the 1/2. And this right here is the airplane. This is the airplane, this little guy here attached to this type A component. So that's the conjecture. We haven't proved it, but that's the conjecture. And the pictures look that supporting the conjecture. And then we have the zero needing conjecture. So if two parameter rays in a needing sequence, in a zero needing region land at the same point, then the corresponding rays in the zero needing, they land in the same point. For example, in this case, you have the airplane region, which is not a rabbit region, and you have the rabbit, 1/3 rabbit over here. And you can see that if you see two rays landing together, for example, 68 and 67 and 68, they also land together over here. And if you count the number of rays that are between 40, 41, and 67, 68, you see that it's the same number of rays in the airplane region. So again, we don't have a proof of that. In a previous paper with Tom Charland and my student Chad Starbrooks, we proved that if you had two rays landing together in S1, you had two rays landing together in S2. But this is a generalization of that conjecture. Independent. Well, in this case, is for no. In this case, it's for fixed P, because this guy is the airplane region in S3, and this is the airplane region in. But it will be independent of P because in the previous paper we did it for S1 and S2. So it's independent of P. Okay. So those are the conjectures I wanted to show you. And then here is the bibliography, in case you are interested. And then I wanted to add some pictures of Karsten. So of people that are close to Karsten's heart and they are not here. For example, we have Bodil, Tanley, of course, Hubbard, I think this is Pascal, right? And here, is it you? Yeah. And then I don't know who is this person here because he's very little, but I don't know if this is Cherita, I don't know. But anyway, here is Pascal and Peter Kaczynski. And you know him, okay? And then another pictures. Okay, so these pictures are thanks to Pascal. She gave them to me. And then I also have here the picture of Karsten by himself. I don't know what he's doing, but he's watching something. And this is Karsten with Eva in Banff during Jack's conference. All right, so this finishes my talk. Thank you for your attention.
Questions?
Thank you, Araceli. You had this picture, you had this conjecture about Mandelbrot copies. And you had a picture there of this Mandelbrot copy, which was kind of very distorted.
Yeah.
Right. So it had the
Airplane.
it had the big rabbit region and the very small other. So do you expect them to be? I appreciate your conjectures that they exist and you can't prove it, but do you expect them to be quasi-conformal copies
Of the
of the Mandelbrot set?
I guess so.
But it must be one of the most.
Unless you want to say something, Jack.
Well, of course we should, I have to unmute. Let's see.
We can hear you.
You're not muted.
Now you're muted.
You were okay, Jack, until you mute yourself. Scott, you have to help him.
Is the operation not invertible?
But Scott is not so far. I don't know why he doesn't get.
You're muted again. You were unmuted for a moment, and now you're muted again.
Jack, you unmuted you muted yourself again.
Now you can speak.
Thank you, Scott.
No, it's muted again.
Good.
Okay, sorry. Well, we should refer to McMullen, his paper on Mandelbrot copies in families of rational maps. This must apply here in some sense, but I'm not quite sure what the conclusion is. But in this example, you see, for example, that that there's sort of a sharp right turn of the Mandelbrot copy where it crashes into an A component. Incidentally, I think this is in S2, not in S3.
No, it's in S3, Jack. It's in S3.
Pardon?
It's in S3.
Well, we can fight about that later.
Yeah, we fight later, but this is S3. Oh, he doesn't hear you.
I mean, maybe it doesn't apply, but I mean, the most congenial way to prove that you would have a QC copy of the Mandelbrot set is to draw the right rays and observe that you have a Mandelbrot-like family. So, I mean, are you saying that that's not so easy in this case, and you need to do something else by hand, and that's why it's a conjecture?
Because we haven't been able to prove it.
You can't. Maybe it's difficult to draw the right regions and so on too.
It's difficult to draw who?
Well, I mean, there's a criterion in the Dwight E. Hubbard paper that if you have a family, if you have a certain winding number condition, then you have a Mandelbrot set up to QC. Well, the QC part came later by Lubitsch, but I mean, once you're in the one situation, you can go in the other. But you do have to look at your parameter space closely enough that you can find an appropriate curve to prove this winding number condition, and I believe that in practice when people do it, they find the curve by drawing appropriate rays and equipotential. So maybe
Yeah.
that's difficult.
But they are in one component. They have only one escape region. And here there are 3 escape regions. 4. Okay, so this is one different escape region. This is a different escape region. This is the rabbit region. This is a different escape region. This is the 100th region, and this is the airplane region. So if you want to compute a winding thing here,
You'd have to do some combinatorics,
Yeah.
certainly, yeah.
Yeah. This is the parameter. This is the curve SP. Yeah. There is a. This is the main component. You were sleeping,
well,
Misha.
so primitive corpus should be all quasi-conformal equivalents, and satellite corpus, so not necessarily, as we know from Karsten and Lunas. So depends on the period.
Okay.
So that is a general answer. So
Okay.
The question is not for satellite corpus. The question is not completely resolved, but in general, they're not
It should be.
quasi-conformal equivalents.
Okay. Good.
Great. We have time for a question more. Well, then let's thank the speaker again. Thank you.
Thank you. And my invitees. Thank my invitees.